Good morning, good evening, wherever you are. Welcome to Turfgrass Epistemology. I'm a little bit kerfuffled right now, trying to get myself situated. Hope everybody's doing well. I am. We have a very full evening tonight. I'm going to have to get going pretty quick here, or I'll be here till 2 in the morning. So, I've been gone all week because the weather here was MLK Day on Monday, and then Tuesday and Wednesday there was some weather here in Lexington, and the school's closed. So I don't broadcast when my kids are here, at least not in the morning. I don't do the morning shows because I'm taking care of kids. And tomorrow they're out of school as well, but I don't do a show on tomorrow morning. So I am here tonight, and then next week I'm gone to Florida. So I will not be here next week at all, even on Wednesday night. So unfortunately, next week it'll be a break unless someone has a creative idea on how to do a podcast from Daytona. So I'm open to that. So, and then the following week, which is the week after next, it'll be the week of January 29th. It'll hopefully be back to normal. And on the during that week, I'll have an author come on that following week. I'm going to go over some more iron things. I have several more articles of iron I'd like to get to, but I know we need to get into some more pressing content and topics. I know you guys are coming up on your orderings and granular fertilizers and so forth. You're looking for some stuff on nitrogen, potassium. I'm aware of that. I'm trying to get to it. So, but regardless, so that's the schedule. So next week I'm out. The following week it'll be a normal week, and then I'll actually have an extra show that week. So anyway, I'll keep y'all updated. I'm doing any updates on the community tab on the YouTube channel. So for those of you listening on podcasts, if you're wondering why there hasn't been a podcast loaded, you can always go to my YouTube channel and check the community tab and see what's going on, because more than likely there's something going on with my kid's schedule or who knows what. So anywho, what else? Wayne Essner. Yeah. Oh yeah. This 500 sub. Yeah. I didn't even realize it. So, I mean, I knew I was in the 400s obviously, but thank you for the congratulations. I guess I hit 500 today. I was saying earlier, when I started, I think I even told my wife, I was like, do you think even 10 people would even watch this stuff? I mean, who would sit and listen to me, meander through my thoughts on turfgrass fertility? But, I was wrong. There's plenty of interest. So I'm glad to do it. So if you guys are glad to listen, I'm glad to do it. So thank you for that, Wayne. Chuck, see you. Travis Tyler. Gray. Oh, thanks. For the Thursday show. Yeah. I did the grass factor last week. So thanks for that. I get, guess it went well. I never really know. So thanks for that. Garden Earth, good to see you. Looney, Ulysses, 500, thank you. Corey, good evening to you. Eric Sands, good evening to you. So we already have a full cast here tonight. Thanks for being here, everybody. I really appreciate it. Like I said, I got to get going because we are loaded. I have 2 videos. I'm not sure if I'm going to do both of them at the beginning or split them, but I got to get started because we have a lot to go over. So let me get to the first video. It's an iron video, and then I'm going to jump to a pH video. Tonight's topic is all about pH. We have an extremely important article to go over. It's going to take me some time to go over it because it's worded in general terms for a soil fertility or for a soil scientist. It's very generic in its language, but it might not be for the average viewer. The average consumer might be a little bit more detailed than you might be used to. So I got to get to it, and I want to get through it because it's immensely important. And so I'm going to spend as much time as I need to feel comfortable that I've explained it. And while we go through it tonight, if there's questions, keep in mind I'm a one-man show here. So if there's questions about the content of what I'm going over, make some sort of notice in the chat, like Dr. Shaddox or Turf Epistemology or whatever, so I know you're asking me the question. And I'll be sure to address that as best I can, because the pH diagram, that content that I'm going to go over tonight, I suspect, could be wrong, but I suspect will be very contrary to what you may believe. Okay, so, and I'm also doing some different things tonight logistically on the show, so if anything screws up or messes up, just, be patient with me as I get through this. So let me get to the video that I'm going to go over tonight. And the video comes from Diano Outdoors is the name of the YouTube channel. The title of the article, or the title of the video, is Flagship Fertilizer with 3% Iron Must See Results. It's very short. I'm only going to show, it's 3 minutes, 4 minute video. I'm not even going to show the whole thing. I'm going to show only portions of it because he just shows himself mowing his lawn. For those people who are listening, it looks like he's out in the country somewhere, maybe in Iowa somewhere, or maybe even Kentucky. He's got a silo in the background, beautiful front yard, maybe an acre, half an acre, something like that. It's pretty nice little yard. Looks like it's tall fescue, striped up, pretty decent. And he's going to be talking about his fertilizer. And this is an example of what I wanted to explain again, what I did maybe the last episode, is what's referred to as the composition division flaw in reasoning. And what happens is because, and it happens quite a bit with fertilizers, where you'll see a tag and you'll see it say 3% iron or 6% iron or whatever the case is. And you'll put it out and you'll see a response. And no one's really going to question that per se if the fertilizer has nitrogen in it. But because the fertilizer also had something else in it, we can't say for sure that the response was due to one thing. And so the composition division fallacy is because you saw a response to the entire fertilizer, and then you claim that it came from just iron. That's a flaw in reasoning. It's a fallacy because we don't know what else in there could have caused it. So just because the fertilizer caused the response doesn't mean every component of the fertilizer contributed to that response. And the YouTube fertilizer garbage that's out there, they take advantage of this. Oftentimes, I think they're just ignorant as well. But sometimes I think I'm convinced that they're not ignorant. They know exactly that iron's not going to do anything. So that's the reason they put in nitrogen. So they know the nitrogen is probably going to give a response. They know that the iron's not going to give a response, but they also are convinced that the iron's going to sell product. So they put it in there, they put it on the label, and they sell. So that's the composition division fallacy. And I want people to be aware of this gentleman. I don't know this gentleman's name, but he's a victim of it. Okay. He's not, I watched this video once or twice, and I don't think that he's contributing to this problem per se. He is by putting a video on YouTube. But I think he's a victim. I see him as a victim of YouTube charlatans, basically, and grifters taking advantage of people who don't quite understand how the fertilizers work and how to identify a certain response from a certain element. Well, let's watch this and see what he has to say, and I'll kind of walk through it as we go.
Hello, everyone. Today I'm out on my newly renovated perennial ryegrass lawn, and it's looking a little weak, a little yellow. I've got a little bit of rust spot in some areas throughout the lawn, and it's just not the deep green that it should be. So today I'm going to apply this Yardmaster flagship fertilizer. It's a 2406 and it contains 3% iron.
Okay, so Yardmaster 2406 fertilizer. For those listening, he's showing the bag. He's showing the label. Well, showing the label. You can't quite read it. I'm going to bring up the label here in a minute. But he's showing it, and for the next minute or two, all he does is go out and he spreads it. I'm going to skip ahead to 2 minutes. I'm not skipping anything necessarily important to the topic. He just puts the fertilizer on the lawn, and he comes back 3 weeks later.
3 weeks ago, I applied the Yardmaster's flagship fertilizer to my lawn. It has a 3% iron in it, which is supposed to help darken it up. Let's take a look at the results.
So for those of you listening, he's showing the results of his lawn, and his lawn looks good. I mean, I wish my lawn looked that good. It looks really good. Nice and green. He's clearly got a, I don't know, probably a 3-foot deck or at least a 2-foot deck on his mower. I mean, he's got a probably pretty good sized mower for that lawn, and it looks really good. Looks good.
It's hard to believe that just a little over 2 months ago, this lawn was completely brown as I started my renovation project.
So he just skipped through there. I don't know what he was showing his lawn there with brown. I don't know if he sprayed it out with a non-selective or what he did here, but it was brown. I guess he killed it out and reseeded it or something. I don't know what he did, but it's very, very common to see a nice, strong response during the first month or two after seeding. And he put out some fertilizer. I'm assuming he seeded it. I mean, clearly it's either, I don't think it's dormant. The crops behind this road here are very green, so I don't think it's just dormant. He probably killed it out and reseeded it, and he fertilized it, and it looks good.
If you guys want to see more of that and how I renovated this lawn, I'll leave a link in the description. Please check it out. As you can see, it looks like it has darkened it up quite a bit. It also made it nice and full.
And I agree. It looks good. I admit. I mean, there's no question, and I would have no worries or concerns about recommending a fertilizer that contained those nitrogen sources. We're going to look at it in a second. The fertilizer was a 2406. I can't remember the ratio there, but 2406, a lot of nitrogen. You're going to see this response. The problem I have is what he says here in just a second or two.
Getting pretty thick. And I did water it in. I applied 1 inch of water from my irrigation system once per week. This is the flagship by Yard Mastery with the 3% iron.
And see, that's what it is. And see, that's what gets people. It's this 3% iron, 2% iron, 6% iron, whatever it is, 20% iron, these really high iron content fertilizers that convince people to put it out. And when they do, they see a response, which reconfirms their initial belief that this will do what it says it will do. It will turn it green because it has the iron. So let's take a look at the label and see what's actually in this fertilizer that could cause or result in a green. So here's the flagship fertilizer label. The 2406. Took me a little while to find this. It's a weird looking PDF for a label, but it's 2406. Here's the 3% iron, just like he said. We go down here, we'll see the analysis, the guaranteed analysis, and it's 24% nitrogen, 21.5% urea. And what we want to look at here is over here in the derived from component, the area. We have polymer coated urea and we have urea. And those are the two urea sources. We have 2% ammoniacal nitrogen that comes from ammonium sulfate. So we have urea, we have polymer-coated urea, and we have ammonium sulfate, and we have some biosolids in there as well that will have some nitrogen in it. But you can see the majority is from urea and from polymer-coated urea. Okay, so it doesn't have much, it doesn't seem like anyway, it has much polymer-coated urea in it, or slow, because it says water insoluble nitrogen. That can both come from the biosolid and from the polymer-coated urea. So it's hard for me to tell from this bag, from this label, exactly how much is urea versus polymer-coated urea. I don't know. But in any case, the majority is from urea. When we get down to the iron, we're going to be seeing three sources. We have iron sulfate, we have iron sucrate, and we have iron EDTA. Now, of those three sources, we know, or we're convinced, hopefully we'll be convinced if you've seen any of the previous videos I've gone over, we've seen numerous papers that have used iron sucrate and iron sulfate. And I think there was only one that showed a response from iron sulfate, and that was in the case where the iron was so deficient that in iron that it wasn't even responding to nitrogen. It was that case where iron was the limiting nutrient, and they did show a response to that application. But in every other case we've shown, there has never been a response to the iron sulfate product as a granule. There's only been responses to iron sulfate applied as a liquid to the leaves. as well as iron sucrate. There has not been a response from iron sucrate. We've shown the solubility of both iron sulfate and iron sucrate in those soils, the solubility of iron in soils paper that I went over. And we also, was that it? Yeah, we also did an extraction with iron sucrate and iron sulfate. 100% was soluble from iron sulfate and acid, and only, what was it, iron sucrate? It was 2 or 3% of the iron was soluble in iron sucrate, something like that. In other words, iron sucrate comes from iron oxide. And because it comes from iron oxide, it's insoluble from the beginning, essentially. Okay, there's nothing in iron sucrate that's going to become soluble anytime soon. There's very little that's soluble. In the case of iron sulfate, 100% is already soluble, and even that source becomes insoluble within about an hour after hitting the soil, in a moist soil, because it oxidizes extremely fast. Okay, so neither one of those sources, here it is, iron sulfate or iron sucrate, neither one of these sources would ever be expected to really, well, with very rare exceptions of iron sulfate, we're not going to expect to see a response from granular applied iron sulfate or iron sucrate. Just forget about it. You might as well just go buy a lottery ticket. You have a better chance of winning the lottery than you would seeing a response from granular applied iron sulfate or iron sucrate. But there is iron EDTA in here. Okay, granular iron EDTA. And if we look down here, we see 0.45% chelated iron. So the total is 3% iron, and of this 3%, so it'd be a sixth, I guess around a sixth of this is chelated iron, EDTA. So one can easily be convinced that, well, it has EDTA. And Travis, you've shown where EDTA does remain soluble for some time after application in some soils. And that is true. We showed that the paper that I did actually, where we looked at all these different soils, and the EDTA can remain soluble in the soil for a week or two or more, but it's all dependent upon the soil pH. Okay. If the soil pH is greater than 7, which is generally when people consider using an iron chelate, EDTA is not going to be a chelate that's going to sustain solubility of that iron at that high pH. It's only going to sustain solubility at pHs lower than 7, say, 6 or 7 or below. Okay. So just because there's EDTA in here doesn't mean that that source is going to result in a turfgrass greening in your case. You have to know what your soil pH is, or be aware of the soil pH. And if it's 6, then you may have a very, very small chance, because you still have to hit the dosage. In other words, the rate of iron has to be high enough to elicit a response. I've used this analogy before. It's the exact same thing as taking pharmaceuticals. Take a Tylenol. 2 Tylenol will more than likely reduce your headache. But if you take just one little fraction of one little granule and put it in your mouth from Tylenol, it's not going to do anything probably for your headache, because you didn't take the right dosage. And in the case of iron and iron EDTA, there's a chance on lower pH soils that it can actually result in a turfgrass greening, but you have to get the dosage high enough. And in this case, if you're applying this product at 1 pound of nitrogen, well, let's just do the math. If you're applying this product at 1 pound of nitrogen, you're going to be applying 4.16 pounds per 1,000 square feet. And you probably need, with foliar iron, you probably need between 1 and 5 pounds of iron per acre, something like that. With granular iron, it varies greatly, but oftentimes it's 20 to 80 pounds per acre. That's very, very high granular rates to get a response from granular applied iron. You'll see that in the literature all over the place, where the rate of the application of liquid iron is 1 to 5 pounds per acre. And of granular iron, it's 20 or greater just to get a response from it. So in this case, you're applying 4.16 pounds per 1,000 square feet times 43 gives you 179. Hang on, I got a dot here. 180 pounds per acre times 0.45. Whoops, hang on. 180 times 0.45%. So 0.005 is around let's just say 1 pound. So you're applying around 1 pound. If my math's right, someone can check my math and correct me if I'm wrong here. But if my math's right, you're applying about 1 pound per acre of granular iron from EDTA. So in this case, you have a chelate that's not really useful above pH 7, and you have an application rate that is almost certainly never going to result in a turfgrass greening. And you have the two other iron sources, iron sucrate and iron sulfate. We're convinced that those, or hopefully you're convinced, I'm convinced that they'll never result in a turfgrass greening under almost any condition. I mean, very, 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 very rare conditions where iron sulfate granular would result in a response. So this is a case where this particular, I'll call him a victim. I mean, this particular victim he's been victimized by the iron misinformation machine. It's the turfgrass industry iron misinformation machine that's been generating and cranking out misinformation for decades. And he happened to get caught up in it and became misinformed and bought the product, put it out, saw a response to it, and was convinced it was from the iron. When you're putting out that much nitrogen, the chances are pretty good you're going to see a response, but it's from the nitrogen, not the iron, okay? So I'm sorry if that gentleman got probably taken advantage of, but he did see a response. It's from the nitrogen. So that begs the question, couldn't you just put out the product and see a response without paying for the iron? That's what I'm trying to get people to grasp, is that the answer is probably yes. You can probably put out, say, whatever I don't know what the analysis would eventually be, 3006 or 3506 or whatever the analysis would be from formulation, where you take out the zinc and the iron and all this other stuff that's in it that you don't need, apply just the nitrogen, maybe a little bit of phosphorus or a little bit of potassium if you see some deficiency in the turf. And you're going to see probably the same response and do it for less money. Okay. So that's what I wanted to do on that video. I got to get to the next video because I can tell this is going to take some time. Any questions in the chat from that video? I will do my best to answer it quickly, but I got to be quick. John Fetter, thank you for the compliment. As my normal audience knows, I will bask. My vanity will bask in the glory of any compliment you want to send me. So, anyway, thank you, John. You're welcome. Welcome. I'm glad you're enjoying the past videos, and I'm glad you can make it tonight. Monkeys, lawn care, and gardening guy. Yeah, pencil and paper. By the way, tonight, the article tonight, you're going to have to put your thinking cap on. Seriously, guys, it's going to take some time to get through it. And to, unfortunately, the topic is rather complicated, but I'm hoping this author has taken the topic, generalized it, and kind of simplified it. And I'm hoping to do it a little bit further to make sure everybody kind of walks away from this video or the PDF tonight, the article tonight, with a basic understanding, or at least you may not be convinced, but a basic appreciation for how what we've been taught, or what you might have been taught, it's not exactly what's going on. So that's my hope tonight. So thanks for coming. Super TA, see you in there. Thank you for your compliment. Yeah, I don't know about that. I'm gonna skip that one. Sorry. I see Ray's in there tonight. EDTA iron calls for 48 ounces of product per 1,000 square feet as a soil application. Of course, less effective if soil pH is over 7. Okay, yeah, it's hard for me to, I'll be honest, it's really hard for me to convert from English. I mean, I can convert with basic stuff from English to SI units, but my brain is so wired for SI units. It's to convert and go, well, 8 ounces is how many kilograms per hectare, and it's it's a little difficult for me to do all that stuff, but I appreciate the comment. Oh, Chuck says the PCU is in the asterisk. Oh, did I miss it? Oh, here it is. Thank you, Chuck. That's what I like mine is for. Catch me. So 12.48 controlled. So okay, perfect. So 12.48%. So if it's 24% urea, so roughly half. So it's roughly 50% from polymer coated urea. Thank you for catching that, Chuck. I appreciate you keeping me on track there. What does that mean, Ulysses? I'm looking forward to the Shaddox Netflix special. What does that mean? I don't know what that means. I hope it's a compliment. I don't know. Okay, guys, let's get to the next video because like I said, I gotta get going. The article is going to take most of my time, and I'm already 30 minutes in. Okay, the next video comes from Ag PhD. Let's take a look and see what Ag PhD has to say.
During our Farm Basics time today, we're going to talk a little about soils. in particular soil pH and how that affects nutrient availability for crops.
Okay, so for those of you who may not know, this is Brian and Darren Hefty. Brian and Darren are evidence deniers. They are base saturation enthusiasts. They are immensely influential in South Dakota. They put on a field day that rivals any university field day. I mean, they have huge sponsors, Bayer, BASF, FMC. They are no small players in the nutrient soil business at all. Don't take these guys lightly. They have a radio show. I believe their radio show may even be on Sirius XM. They are huge. They put on a conference. They have winter conferences. They have just a tremendous footprint and platform in soils. They're almost always in ag. They rarely kind of venture over into home lawns, but occasionally they do, which is one reason why I'm showing this video tonight. We're talking about pH, and they're going to talk about pH right now. And I'm going to let them kind of make their claim and then explain to you using the evidence how this sort of propaganda is so immensely important to identify and squash. They have a tremendous impact in our industry. They have big money, hundreds of thousands of dollars they pull in on their field day. It's enormous. And, they're no small players. So let's look and see what the rest of this video has to say about pH.
What's fun this spring and early summer is getting soil tests from across the country and in different situations. Now, for example, one of the things that we saw was low micronutrient availability, and one of them in particular was manganese. Whenever we would see a 7 pH or higher especially, or even some of the upper 6s, we saw lower levels of manganese on many of the tests.
Yeah, and so this is very common. Okay, this happens. I'll notice this as well. Okay, it's just an observation. It's solely anecdotal. Okay, there can be cases where manganese is low at low pH. There can be cases where manganese is high at low pH. Okay, there's more going on in the soil than just pH is low, therefore manganese is more soluble. pH is high, that way, therefore manganese is less soluble. There's a tremendous amount of dynamics and interactions going on in the soil. And just because the pH is low on this soil test and you see it correlate with a high manganese concentration does not necessarily mean that you should maintain this lower pH. And I'm going to explain why, and hopefully the authors of the paper tonight are going to explain why that is. Okay, let's get back to the video.
And when we saw lower soil pHs like low 6s, upper 5s, we saw higher availability of manganese.
So again, availability is usually it's a phrase, at least for me anyway. It's a phrase that I'll catch in language that it's not. Sometimes it's just misspoken. Like sometimes I'll just misspeak and use that word. Maybe he just misspoke and used that word. I don't know, but we just generally as soil scientists don't say available, plant available. I don't even know what that, I mean, it's just not a soil chemistry word really, or phrase. It's it's soluble or it's insoluble, it's exchangeable or it's non-exchangeable, or it's an organic element or bound with organic ligands or whatever the case might be. But to say it's plant available takes a tremendous leap of faith to be able to say that. And so when you hear these words, I was like, there's just little bitty points that I'm hitting in my mind going, if I didn't know Darren, or I don't know either one of them, but I've seen some of the videos. If I didn't know Darren or Brian, I would be thinking, oh, wait a second. He may not know what he thinks he knows here, but let's just continue.
Do you see a correlation here with soil pH and potential nutrient tie-up?
All right.
So soil pH and potential nutrient tie-up. The BS, you're gonna have to hike your boots up here in a little bit. Okay, the BS starts to flow. I'll just say that.
And I want to give you a very specific example with one of the primary nutrients, phosphorus.
Okay, so here comes the BS. I don't know these guys' backgrounds. They may be the world's greatest soil scientists and phosphorus bioavailability experts. I have no clue. But when the next couple of sentences, when he says this, think to yourself, when he says these things, I'm gonna stop it. And I'm gonna go back to a article. Think to yourself, did I also think that way? Or that what he said it sounded correct to me. Think if that's what you think, you're in the boat with a lot of people. Very common. Okay, here we go.
What happens with phosphorus is it's usually in the phosphate form, and in high pH soils, there's typically excess calcium. Well, calcium can bind with phosphate to form calcium phosphate, which unfortunately is insoluble in water. When it doesn't dissolve in water, that means the plant can't bring it in. It's not in a form the plant can use. So it's all because the soil pH gets so high, and then we start seeing that excess in calcium and the binding with phosphate. Now, the same thing can happen with phosphorus when we get to the low pHs. So that calcium thing happens predominantly in the 7.5 to 8.5 range for pH. When the pH is low, let's say it's down in the 5s, we'll commonly see phosphate binding with iron.
Okay, so this is what's referred to as the double sink. Okay, there's very little evidence to support this idea that phosphorus will bind with calcium at high pH and iron and aluminum will bind with phosphorus at low pH, and therefore there's a sink at both ends of the pH spectrum. I'm going to go over that tonight, okay? But if you heard what he said, he's basically saying that, well, he's not basically saying, he's saying that you need to keep phosphorus, you need to keep the pH, in this neutral to slightly acidic range for maximum phosphorus availability, because there's a sink for phosphorus at the high end due to calcium, and there's a sink for phosphorus at the low end due to aluminum and iron. And if you also have heard that, or you're in the position where you believe that or whatever, you're in the same boat with a lot of people. Okay, well, we're going to explain tonight. I'm going to explain here in a couple of minutes on this next PDF why that just doesn't hold water in the world of soil chemistry.
When the pH is down in the 4s, we commonly see phosphate binding with aluminum. Well, in either case, there's phosphorus in the soil, but unfortunately it's binding with another nutrient, so the plants can't get it and use it. That's a real problem. By simply getting the soil pH in the appropriate range, let's say around 6, 6.5, 7, somewhere in that range, phosphorus becomes a lot more available than it is when the pH is too low or too high.
Yeah, see, this is just simply not true. I don't know who these guys are, Brian, and Darren, I don't know their background, but they just don't know soil science when it comes to phosphate availability or solubility. They just don't understand it. So, and I'm not claiming I do. But we're going to go over two articles tonight. We're going to briefly go over one little article. It's going to take just a minute or two. And then we're going over the big article. And they're going to show where phosphorus availability is not maximized at this 6 to 7 range. Okay? We're going to get there. Let's continue.
Now, if your pH is too low, one of the easiest ways to raise that pH up is by applying calcium carbonate. This is something that could be used in your lawn. It could be used in fields, certainly could be used in gardens as well. One spot in particular I'll point out for your lawn is if you have a dog and that dog does his thing out in your yard and you have little spots in your yard that are dying. The cure for that is lime. It's calcium carbonate.
Now, I don't know if I'm sure there's research on turfgrass dying from dog urine. I'm sure there's research somewhere. But I'll admit a little bit of ignorance there. I don't know all the chemistry behind that. I always assumed that it was dead because of the salt content of the urine, not because it's influencing the soil pH. And what he's saying is you should apply lime. Let's see this again.
Raising the pH up can fix that problem. It does his thing out in your yard and you have little spots in your yard that are dying. The cure for that is lime. It's calcium carbonate. Raising the pH up can fix that problem.
Now, maybe someone can post something. I don't know. I've never heard that. Raising the pH of your soil can fix dog urine stains or death of your turf by dog urine. I've never heard that. I don't know if it's true or not true. I just always have been it's always been explained to me that the death of the turf was a result of the burn of the urea, the salt content of the dog urine itself. But I could be wrong. So, but he included that in turf, so it's fair game for me to show. That's the reason I'm showing this video. Let's continue.
Because what the dog left behind was very acidic. So acid is the key if you wanted to lower a high pH. In fields, we usually talk about improving drainage to flush salts out. Generally speaking, when we have more salts and more sodium, that pH starts to climb. That can be a real problem.
Of course, improving that drainage is important. And then one thing that you could apply in high pH situations in many cases is elemental sulfur. That can help form sulfuric acid in your soil and lower that pH back down.
Well, once again, the pH of the soil has an enormous impact on availability of nutrients. I gave you the example of phosphate in low pH, high pH, and neutral pH, but the same types of things can happen with just about any nutrient out there. So as farmers, and for that matter, if you have a garden or a lawn, whatever, you want to try to get that soil pH around that 6 to 7 range for most crops, most lawns, most situations. But I will say there are certain crops, they prefer a little bit lower pH, others like a little higher pH, and that's one of the things we commonly talk with farmers about.
Okay, so he qualified himself at there at the end. Most soils, most crops, most this. It's 6 to 7s for most and most and most. So you qualify yourself there. We're going to go over tonight an article, like I said, but this is just a general phrase that has been so driven into our minds that I doubt there's many people listening to this show tonight or on podcasts that disagree with that statement. I doubt there's many that would disagree with that statement, except me. And the authors of the article that I'm going to show tonight. I'm going to explain why moving pH could end up screwing stuff up. Okay, let's look at the article. What his claim was at the what was it? The middle of it was that high pH phosphorus will bind with calcium, low pH phosphorus will bind with aluminum and iron, and so the maximum availability is somewhere in the middle. So if we go to this article, I'm not going to go over this article right now. I'm going to go over this article in another maybe even next or 2 weeks from now, on a Wednesday night. I'm not going to go over this whole article right now. The effects of pH on phosphate uptake from the soil. This is by an author named N.J. Barrow, who's in Australia, been there for ages and ages and ages. And what he's talking about, the Darren O'Brien, whoever said that, he's talking about this graph where we see phosphorus being bound with calcium. When you get up to 7s, 8s, and 9s and above, you see this binding amount of phosphate fixation being highest at these high pHs from calcium. And you see once you get below 7, you see aluminum and you see iron binding phosphorus at the lower pHs. So he's talking about this figure right here. Okay, there's been many reproductions of a figure very similar to this. It could be slightly adjusted here or there, but that's the basic idea, is that fixation of phosphorus by calcium at high pHs and iron, aluminum at low pHs is maximized at these low and high pHs. And in the middle, right here, it says range of highest phosphorus availability right here. Okay, that's what they're talking about. Okay. So I'm going to go through this whole article at some point in the future, but not tonight. What I'm going to do is I'm going to scroll down here. I'm going to read the conclusions, then I'm going to go back to I think there's 2 figures. Yeah, right there that I'm going to go over. But here's the conclusion. The very last paragraph of this paper says the following: soil pH affects the availability of many nutrients and of several toxic elements. And that's what I want to make sure it's clear tonight. I'm not saying it doesn't affect the solubility of it, and neither are they. We're not saying that at all. It does affect the availability of nutrients. pH does do that. Okay, I'm not saying it doesn't. The optimum pH for plant growth depends on which of these elements is most limiting. So if phosphorus is not the most limiting nutrient and you try to adjust the pH down, up or down to make phosphorus more available, but it's not the most limiting nutrient, you could be altering the availability of the element that is most limiting. Okay, we're going to go over that. This was shown in figure 10b. Well, I'm going to go over that in a minute, in which clovers were limited by phosphorus supply, but the grass was limited by the nitrogen supply. Consequently, the optimum pH differed. This illustrates the kind of evaluation needed in many practical situations when deciding what pH to aim for. Raising the pH to, say, 6 to 7, which is what he just said, I'll say 6 to 7, somewhere in like that. Raising the pH to say 6 to 7 might be justified for several reasons, but increasing the availability of phosphate is not one of them. That is one of the most profound sentences I've probably read on this channel. Let me read it again. Raising the pH to say 6 to 7 might be justified for several reasons, which I agree, might be justified. But increasing the availability of phosphorus is not one of them. Let's go up here and look at these two figures. In this figure, for those listening, we're looking at two different panels of the same figure. Both panels have the x-axis going from pH 4 to 8. And on the x-axis is 4 to 8. The y-axis is yield of tops, grams per pot. And one of the panels, we're looking at two species of clover and then one species of lolium species. And I forget this species on this one here. This was trifolium. Okay, so this was also a clover, I believe. So this is all clover, and then this is clover and lolium. In this figure, we see pH go from 8 to, well, let's say 7, okay? And the scientist is applying either no phosphorus, 50 milligrams per kilogram, or 100 milligrams per kilogram of phosphorus to clover that is not deficient in nitrogen. It's a legume. Okay, it's not going to be deficient in nitrogen. When we see the pH decline from 7 to 4, we see the yield peak, not really do much. It kind of goes up from 7 to 6 on this no phosphorus applied, but we see it peak from about 5.5 to 5, and it peaks here at 5 when no phosphorus was applied. When you apply phosphorus, it goes the yield also peaks. It goes up from 7 to 6 as well, but it peaks at around 5. And when you apply 50 grams per kilogram, when you double that, it also peaks at around 5. The yield of clover that is not nitrogen deficient peaks at a pH of 5 because it was phosphorus deficient, meaning or indicating that the greatest uptake of phosphorus did not occur between 6 and 7. It occurred at 5, much lower. Okay, now let's look at the next panel over here, panel B. We see 2 clover species, and we see 1 lolium species. This species here is not a legume. It has to be fed nitrogen, basically, in order to be, well, in this case, it's probably yield. But as the pH goes up, we see the yield of this lolium species continue to go up, clear up to 7, whereas the yield of the clover goes down from 5. There's never a point where it just continues to go down and down and down from 5 to 6, from 6 to 7, the yield of this non-limiting nitrogen species, the clover. So why did this species go up and this species go down? The yield go down on the clover, but the yield went up on the lolium. In this case, when the pH is going up from this lolium species, there's more organic material being mineralized as the pH goes up from 5 to 6 to 7. There's more nitrogen being mineralized, which I'm going to show you in the very next article. Okay, so as we move the pH up, more nitrogen is going to become more available between 5 and 7, because assuming you have some appreciable amounts of organic material, because the organic material is going to be mineralizing nitrogen and it's going to become available. But with the clover, it didn't matter because it wasn't nitrogen deficient. Okay, so the maximum uptake yield as a result of phosphorus occurred at a pH below 6. Okay, that's the point that I'm trying to make, is that these two, Brian and Darren, the two evidence deniers who spew unbelievable amounts of nonsense when it comes to base saturation and calcium, and just, I mean, it's insane, and they have a tremendous impact. They are not two guys sitting in their, closet, not, just fiddle-faddling around. They have a tremendous impact and influence. They are highly influential, and they're spewing all kinds of nonsense. And they're saying that because calcium is binding a phosphorus on the high end, and because aluminum ion is binding phosphorus on the low end, you should keep the pH between 6 to 7, specifically for phosphorus uptake. And the evidence I just showed you clearly indicates that that's not true. Okay, So please be mindful of that. And that's going to lead us into the article tonight. Okay. All right. So let's look at the chat one more time before I get started, and I will get going. Yeah, Western Master. So the cure is immediate irrigation. Yeah, I mean, I admit my ignorance when it comes to dog, spots, but I'm assuming if you just irrigate it and water it off, or I'm assuming it's a salt problem, but I could be wrong. So here's Ray says pH has nothing to do with that. I can always tell a lawn on too much by how it acts when there's a dog here. Yeah, well, yeah, maybe. Yeah, elemental granules, John Federer, elemental granular sulfur lowers pH very slowly, like months to years. Well, it's going to depend on the soil in that one, John, but it's possible in heavier soils and low rates of sulfur. It could, but sulfur is definitely something you don't want to mess around with. You need to know what you're doing when you have sulfur in your hand. You can kill some plants real quick, or you can make them look great. You got to know what you're doing. Okay, so now with all that, we will get into the most important article I think I've probably gone over in this whole show. The effects of pH on nutrient availability depend on both soils and plants. So, if you're unfamiliar with the topic or the concept of what I'm going to do discussing tonight, I'm going to pull up, I'm just Googling pH diagram, it'll pop right up. Yeah, popped right up. So I'm going to pull this up just so we're 100% clear on what exactly I'm going to be talking about tonight. This diagram, I'm sure many of you have seen it, been familiar with it, is very common. You can go on any YouTube, Turfgrass, someone selling you something, they'll have this diagram on there. This is another red flag for me when someone's saying availability of nutrients, plant availability, that's a little red flag. When someone throws this up on the screen, you can bet your farm that they don't know what they're talking about when it comes to soil pH and nutrient availability, because this diagram has done more damage to our industry probably than anything I can think of. There's just been so much wasted lime and wasted sulfur and all sorts of stuff trying to move this pH number all over creation. And just to set the stage that everybody's on the same page, the idea is that because we see, for those listening, I'm showing the pH diagram where the nutrient availability declines for some elements as we become more acidic. It also declines for some elements as we become more alkaline. And so the concept or the idea is that we want to maintain the slightly acidic soil pH for maximum nutrient availability. Okay, that's what this tonight's about. All right, so let's get back to the article. When it comes to the article, I'm gonna have to read a lot of it because I don't want to miss anything. But I'm gonna read the abstract, because the abstract alone. By the way, I think this article is for free. It's published in Plant Soil in 2023, and it's by Barrow and Hartemink. And this is the gentleman in Wisconsin who's insanely cited, and this is the gentleman in Australia who's, I think, probably in his 70s or 80s now, and done some great work since the 60s. I'm going to read the abstract word for word because it's immensely important. The abstract: the effects of pH on nutrient availability are not solely caused by the effects of reaction with soil, but are an interaction between these effects and the effects on rate of uptake by plants. So I fumbled through that one. Sorry about that, guys. Some effects are specific to particular ions, but an important aspect is that plant roots and soil particles both have variable charge surfaces. This influences availability, but in opposite directions. Sulfate is an example of this interplay. Its sorption by soil decreases markedly with increasing pH, and thus soil availability, in quotes, notice he put that, these authors put soil availability, because we just don't really use that too much. I like the fact they put it in quote marks. Sorry, markedly with increasing pH, and thus soil availability increases. However, plant uptake also decreases with increasing pH, thus plant availability, again in quote marks, decreases. For phosphate, the plant effect is stronger than the soil effect, and the uptake decreases with increasing pH. In contrast, effects of increasing pH on molybdenum adsorption, are so large that they dominate the overall effect. Sorption of cations such as zinc or copper increases with increasing pH, but uptake rate also increases. The net effect is a small decrease in availability with increasing pH. Boron is an exception. There are small effects on pH on sorption, and it is the uncharged boric acid molecule that are taken up by plant roots. Their uptake is not affected by charge, and uptake is proportional to the concentration of uncharged boric acid and acid molecules. We argue that emphasis on the effects of pH on reaction with soil has led to a distorted picture of the effects of pH on nutrient availability. So what they're saying is, if all you're going to do is look at soil pH and how it affects the solubility of an element, you are grossly undersimplifying the whole process. There's more going on when it comes to the actual plant uptake of that element than just soil pH. And that's what I think, if there was one thing I would say that, well, I would say about this article, and I don't know if the authors would say this, is that I don't care about the soil solubility of an element. What I care about is the plant uptake of that element. Now, I understand the plant uptake can't occur unless it's soluble. I get that. But it's the plant uptake that diagram does not include. It's the plant interaction with the soil that diagram does not include. There's interactions with other elements. There's sorption and adsorption with the soil. There's all sorts of other things going on in the soil that are not included on that chart that we need to account for. As I just showed you in the previous video, there's a case where when the pH goes down, the yield of some plants will go up even below 6 in the case of clover. But if you're growing lowly and perenne and you're like, well, I want to increase the yield, so you're growing hay or something or whatever, and you want to lower it from 6.5 to 6 or 7 to 6 or whatever, you're going to reduce the growth rate because it's nitrogen limiting. It's not phosphorus limiting. So the nutshell of tonight's talk is moving the pH, one, is most likely futile. I mean, it's in many cases unnecessary. But if you're trying to move the pH to target the solubility of a specific element, you better be sure that that's the element that's limiting. You better know that it's a phosphorus deficiency if you're going to lower the phosphorus from 6.5 to 5 or 6.5 to 5 or whatever. Because if it's not the limiting nutrient and you try to adjust the pH, you could be actually causing more problems, which is, again, a further example of why I say don't do things unless you have a good reason. It's the lion, the mouse, and the cheese analogy of the book, where you're doing something and you think you're doing something good and it causes another problem. And now you got another problem to deal with. You lowered the pH on the lowlium species. You lowered the pH when in fact raising the pH would have resulted in the greater yield rather than lowering it. But you lowered it. Now you got a reduced yield. Now what do? You apply more nitrogen because you need more nitrogen to push it up higher. It's just it's a hamster wheel of endless poor logic. So don't do things unless you have a good reason. That's key. Okay, let's continue. The introduction. Soil pH is considered to be the master variable, and quote marks, by the way, of soil chemistry due to its profound impact on countless chemical reactions involving essential plant nutrients. This is the opening statement of a paper which the authors considered are presenting the classic understanding of the effects of pH on P uptake. We quote it here because it illustrates a common attitude. It emphasizes the effects on soil chemistry, but scarcely considers the effect of pH on the rate of uptake of nutrients by plant roots. This is a fault that is not limited to that paper. Okay? So they're basically saying this is common, not only in marketing and not only in, all this other, misinformation, propaganda machines. It's common in the scientific literature. Someone will just say this stuff. It's the master variable, and they're saying this is common. We quote it here as an example. This exists in the scientific literature. We continue. In an accompanying paper, which is what I went over last week, we discussed a conceptual soil pH nutrient availability diagram that purported to show how the availability of major and minor nutrients was affected by the pH. The diagram has been published in textbooks and soil extension materials and continues to be used as a teaching tool. We argue that the diagram was simplistic, which I agree. One of the aspects to which it plays insufficient attention was the effect of pH on the uptake of nutrient by plant roots. Here we show that these effects can be large. The relevant information is somewhat scattered. In this article, we attempted to bring plant and soil information together to bring an overall picture of the effects of pH on the availability of both anions and cations. Penn and Cambarato, 2019, write that ligand exchange is not dependent on surface charge. Here we start by explaining that surface charge, or more appropriately, surface electrical potential, is an important influence on the effect of pH on reaction of ions with soil. So they made a case. This is what we're going to talk about, right? Okay. Now, when they talk about variable charge, what I want to explain, I don't want to get too far off in left field if it's too much for you guys, but they're going to talk about variable charge and permanent charge. Let me think here. How do I want to do this? Let me just read it, and then when I get to it, I'll stop and explain it. It is not elements that react with soil. It is ions, and ions bear charge. We therefore need to understand the charge carried by soil particles. Soil scientists have long understood that clay minerals bear a negative charge that is caused by isomorphic substitution. Well, so I should have just explained it from the beginning. Okay, so permanent charges are charges on soils that are not influenced by pH. Just think of it like that. They're permanently a component of the soil. And isomorphic substitution occurs when that mineral is formed, whether it's formed in a volcano or through a geologic process. It's when that mineral was formed, there are layers, silicate layers, and in the silicate layer, there's a structure, okay, that have certain elements in it. But occasionally, when that clay is formed, there'll be one ion in the clay lattice that is substituted for a different ion. And when that substitution occurs, it's called isomorphic substitution, and it results in a net negative charge on the surface of the clay. And because that element is inside the clay structure lattice itself, it's not going to be removed, and therefore the charge isn't going to change. You can have the pH, whatever it is, and that permanent charge is still going to be there, okay? That's what he's talking about when he says isomorphic substitution. These are known as permanent charges. However, clay minerals are rather unusual crystals in that the faces do not have atoms with unsatisfied bonds. For example, for the surface of most crystals and for the edges of clay minerals, atoms do have unsatisfied bonds. The classic example is silver chloride, which takes up either silver or chloride ions, depending on which is the present in excess and therefore has either positive or negative charges. These ions are therefore the charge determining, or we can also say the potential determining ions. Okay, so what he's saying there is, envision the clay that has isomorphic substitution between the layers, the lattices. Those charges aren't going to change, but on the edges, when they're broken and shattered, and there's exposure to the clay lattice on the edges, those charges can be changed. They can either bind cations or anions depending on what's in the soil, where it's at in equilibrium with other ions in the solution. Okay, this is going to become important. I'll get to it. For oxides, the edges of clay minerals, the unsatisfied bonds, which is what I'm talking about, the bonds that are on the edges, okay, this results in links to water molecules. These gain or lose protons depending on the pH, and thus the charge and also the potential varies with pH. Okay, so when it comes to the what he's talking about is the CEC. The CEC of the soil, or anion exchange capacity of the soil, depending on the soil, is permanent when isomorphic substitution occurs, or it can be variable depending on the pH under certain conditions. Okay, so the retention of ions, whether it's cationic or anionic, the retention can vary depending on pH. But there's also a large portion of the CEC, or anion exchange capacity, depending on other things, but almost always CEC, is that component is not influenced by pH. Okay. In shorthand, they are variable charge substances. Okay, that's basically what he's saying. He summed all this green stuff up, which is rather generic, soil chemistry, soil mineralogy, by saying they have variable charge surfaces on the edges. Okay, I'm going to skip to the green part here. Soil color, though easily observed, is a complicated property depending partly on organic matter and partly on the oxide's presence. And he's going to talk a lot about iron oxides in this paper, The reason he talks about it is because oftentimes when we do sorption isotherms, or we want to know how an element engages or interacts with the soil. Oftentimes we'll use like a pure system, and oftentimes we'll use like an iron oxide system. So he's going to talk a lot about oxides, and then he backs up and says soils aren't oxides. They're not a pure system. So I'm going to get to that when we get to it. Iron oxides are an important contributor to soil color, with goethite tending to be dominant in cooler, damper soils, and providing yellow-brown colors, and hematite tending to be important in hotter, drier soils and providing reddish colors. The important interpretation of this is that variable charge materials are present in just about all soils. Their presence is important in determining the effect of pH on reactions with nutrients and interpreting pH. So what he's saying is very simple. It doesn't really necessarily matter what the color of the soil is. pH-dependent charges can exist in all soils. And you need to be aware of that if you're going to use the soil pH diagram, or you're going to start adjusting the soil pH as a means to result in some desired outcome of the plant. You need to know that, this is a dark soil, so it's going to have more pH-dependent charges than that soil. No, all of them can have pH-dependent charges, regardless of the color. You can't just look at a soil and say, that's a pH-dependent, that's going to be high organic material, so it's going to be high pH dependent, and this one's not because it's brown and red or whatever the case is. That's basically what he's saying, okay? Although we speak of soil pH, the term is strictly, this is funny. Hang on. This is actually funny. Although we speak of soil pH, the term is strictly speaking nonsense. These guys are kind of like myself. I like using that phrase, nonsense. Strictly speaking, soil pH is nonsense. pH is a property of liquids. It's not a property of solids. I like the way they just say it in such common language. It's nice. What we measure is the pH of a solution in contact with a soil, and the answer we obtain depends on the solution we use and not on the net charge carried by the soil. So we do soil pH measurements in various liquids, water, calcium chloride. There's all sorts of different buffers that can be used. We do it when 2-to-1 soil to water. We do it 1-to-1 soil water. We've seen 10-to-1 water to soil. So there's all sorts of different ratios and solutions, but what they're saying is soil pH it's nonsense. So the soil itself doesn't have a pH. It's the soil solution that has the pH. Okay, go down to the red. Commonly, soil pH is measured after mixing soil with water. This decreases the electrolyte concentration in solution and results in a higher measured pH than would be appropriate for the soil solution. So very simple, very straightforward. He's saying that when we mix it with water, the water is probably neutral, 7. When we mix it with water, we're going to result in a higher pH than what exists in reality. What exists in the soil solution, or in around the root zone, and even worse around the root zone, the Risosphere, that's the soil pH we measure is not going to be representative of that. I mean, you can probably correlate it if someone's done the correlation, but just because we do a pH on a soil test and it says, it's 6.5, that doesn't mean that's what the pH of the Risosphere is. Doesn't mean that's what the pH of the soil solution is. Okay, if there's a strong correlation, then we can make that argument. Okay, but he's making a case saying that it's, when you're talking about solubility of the element, I want to know what the soil solution pH is, or the Risosphere's pH is, right? Okay, so this next one here, I may end up skipping over because it's a little bit much. But basically, what I wanted to say here in this next section, the effects of pH on adsorption of anions. This section here, I'm going to leave you guys to read this on your own because I'm already an hour into this thing. And quite frankly, I didn't even highlight it. Basically, it's saying what I've said in the past about building models for turfgrass science. What he's saying here in this whole section that I have not highlighted, I just highlighted the section heading, is that in the past, the soil scientists have had different models to predict what they expect to occur from soil pH measurements. And those models have changed over time. They used one model and it didn't account for everything. So then they had to make an adjustment and that didn't account for everything. And then they had to make another adjustment and that didn't count. So they eventually keep working and working and working on it. And they've refined the model down to where it's usable and it's used to make predictions. And as I've said in my past videos, the evidence comes in that's new evidence, but reality doesn't change. Reality is just reality. The evidence is our best manner of determining what is going on in reality. We get new evidence comes in, but the model has to change. Okay, new evidence comes in, reality never doesn't change, as far as I know, at least not my reality. But we have to change the model to make it fit. The model must make predictions and it must fit. And if it doesn't fit, we have to make a change. So he goes through like 2 or 3 paragraphs here, basically explaining that concept in soil mineralogy and soil chemistry. And you're welcome to go back and read that if you want to know more about it. I'm going to skip down to this next section on page 25. The binding constants of different ions are related to the appropriate dissociation constant of the relevant acid, figure 4. I'm not going to show figure 4. This can be interpreted as showing that ions that have a strong affinity for protons also have a strong affinity for the electrophilic metal ions of the oxide surface. So as I mentioned as I started here, a lot of what we do when we do isotherms, or we sorb ions onto a soil and we see what it takes to get it off, and we see how pH influences that. It's done well, at least initially. They're done oftentimes in pure systems with oxides. And what he's saying here is that the ions that have a strong affinity for protons also have a strong affinity for the electrophilic metal ion of the oxide surface. So they're doing these sorptions on sometimes iron oxides, okay? That's the reason I'm kind of skipping through this, because I don't know how relevant it is for what we really want to know. Relevance to particular ions. An ion can dominate the reaction even though it is a minor constituent if its binding constant is large enough. Okay, so just because you have a little ion in the solution, I go, well, that's a small one, and I'm dealing with this massive phosphate ion or whatever, it's not going to have an influence. That's not always the case, as they're going to show here, okay? Consider the monovalent and divalent phosphate ions. The first and second pK values for phosphoric acid are about 2 and about 7. From figure 4, the binding constant for divalent ion will be about 10 to the 5th times that for the monovalent ion. Then, even at pH 4, when there are about 10 to the 3rd monovalent ions for every divalent ion, the product of this alpha K, which is in this equation over here, I'm not going to go into that, but you're welcome to. He explains all the components of it. Will be about 100 times more favorable for the divalent ion. This explains why a minor constituent can dominate adsorption. Okay, so if you want to know how little guys can make big impacts, this equation explains it. Again, I'm skipping through this. I'm just trying to get to the more important stuff that you guys might be interested in. Okay. The value of the potential depends on several factors. One is the size of the ion. Fluoride ions are about the same size as hydroxyl ions and are therefore located at the surface and experience a large change in potential with pH. The phosphate ion, the mean center of the charge, is further from the surface, and the charge and the potential with pH is smaller. So what they're saying is that basically if you have let's say you have a beach ball and the charge is in the center of that beach ball, the distance to the outside of the element is, say, 6 inches or 7 inches, versus let's say you had an element the size of the earth and the charge is in the center of the earth. The distance to the outside is much, much, much further, and therefore the binding power, if you want to call it that, is much less from the larger ion, because the distance from the charge is so much further away. From the smaller beach ball size element, it's much closer to the surface and therefore might have a greater impact. Another important factor is the nature of the solution surrounding the particles. Increasing its ionic strength compresses the diffuse double layer and decreases the rate at which the potential changes with pH. This is an important reason why it is difficult to make a simple statement about the effects of pH on adsorption. Okay? So it's not just the element, it's the element size, but it's also the nature of the solution surrounding the particles. There's a lot going on. So just to say, the pH is this, and so you're going to have this much influence on adsorption, it's not that simple. I'm going to skip through a whole lot here. I'm going to get back to pH 7 because it's going to this goes back to the adsorption of phosphorus. So I'm going to show you in just a second, I think. Okay. Actually, you know what? Let me show that right now. So this figure 7, effects of pH and time on sorption of phosphate by a soil. Okay. The sorption, 1 to 30 days. For those listening, it's a pH of in calcium chloride from 3 to 8, and then P sorbed at a unit concentration. And we see the maximum sorption occurring at, let's see, P sorbed at a unit concentration. Yeah, so the minimum sorption occurs between, say, around 6 is the minimum, the amount sorbed on the soil, and the maximum amount sorbed as it goes from 6 to 3, and it goes even up from 6 to 8. What does this mean to you? When an element is sorbed onto the soil, it's not going to be available to be taken up by the plant roots. And at a pH of 6, right here, right, this is where the minimum is sorbed. Okay, the maximum is sorbed as we go from 6 to 3 or whatever. Am I reading that right? P sorbed at unit concentration. I don't know if I'm reading that right here. Let me back up. So 1 day. Oh, okay. So this is 1 day. And no, 30 days. So it keeps going. Okay. So the sorption is greater as you keep going days and days and days. Okay. So 30 days. So the longer it goes, the sorption is greater. And the minimum sorption for that particular time frame is around 6 to 5, something like that. Okay. So this range right here, this 5 to 6, maybe even 7, you could even go to 7, relates to the uptake from the other article we showed, where we're talking about the maximum plant growth was at 5. And so we have a range here where the P sorbed is the least between, say, 5 and 7, something like that. But it's certainly not, you can't just say, well, 6 to 7, you're good. Well, you're also good from 5 to 6 in this particular one. I mean, it's basically splitting it between 5 and 7. Okay. That's what I wanted to show. Now we're going to continue. Sulfur sometimes seems, oh, this is funny because I'm dealing with sulfur right now. I'm writing an article on sulfur. Oh, I'm waiting for the last batch of data to come in. So whenever someone talks about sulfur, I get all excited because I don't know a whole lot about sulfur. I'm doing my best to educate myself on it. But when you use a psychological, or I guess it's psychological term to discuss soil nutrients, it just for some reason gets me. I've never heard sulfur referred to as schizophrenic, so I like this. Sulfur sometimes seems like a schizophrenic nutrient. I don't know, for some reason I love that. That's great. It has two personalities. In some soils, it acts as a specifically sorbed anion. In others, sulfur supply is governed by mineralization of organic sulfur. In Australia, soils that sorb sulfate strongly are found in high rainfall areas and are derived from basic rocks. Examples occur in the north coast of North and South Wales. In southeastern Victoria and in southwestern Western Australia. Examples occur in the north coast. Okay, and then, give examples. Sulfate sorption is marked on andisols. These soils have elevated contents of short-ranged ordered minerals and are insoluble aluminum humus compounds. It is also marked in a highly weathered soil, such as oxasols. So andisols, if I'm not mistaken, are a dominant soil classification in places like Hawaii, Peru, probably even parts of like Colorado, and I imagine probably Colorado and Wyoming, those areas over there. And what he's saying is sulfate, it acts differently in the soils. And in the cases where you're dealing with sulfur absorption on high pH, is probably due to the mineralization of organic material. And I'm going to show you that in a second. But sulfur absorption can occur at different pHs. It's schizophrenic. I love that. That's great. So sulfur absorption sulfate strongly are found in high rainfall areas and are derived from basic. Yeah. So okay, good. All right, let's get to, there's a really good graph in here with sulfur and nitrogen and carbon. I think it is. I'll get to it. I don't want to miss it because make sure I get to, I don't want to miss that thing. Where is that? Oh yeah, I'm coming up on it. It's in figure 12. Okay, I'm getting to it. Okay, the effects of pH on adsorbed cations. So we're talking about calcium and magnesium and these things. Oh, I guess he skipped through that. Here's what I'm looking at, guys. They're showing a lot of different things here. Okay, let me just skip through. I highlighted this down here for a reason. The effects of rate of reaction. Chemists tend to think in terms of equilibrium, but farmers and agricultural scientists know that nutrients react with soils for a very long time, and as a result become less effective. We are aware of only one study on the effects of pH on rate of reaction. Figure 7 shows that for phosphate, the continuing reaction is fastest at low and at high pH and slowest in the medium pH. This means that the effect of pH on sorption becomes increasingly U-shaped, a further indication of how difficult it is to make a simple statement about the effects of pH on phosphate sorption. So let's go to figure 7. Or did I just show that? Yeah, I just showed that. So what he's saying is that if you're going to assume you need a lower pH, well, to what? All right. I mean, if you're, let's say you're 6.5 or let's say you're 7 and you want to lower it, or you're 5 and you want to raise it. Like I've said before, why? With the particular issues with phosphorus, you may end up raising it too high. You may end up lowering it too low, right? I mean, it seems to me like 5 to 7 is probably a decent range, maybe even 5 to even higher. I mean, 5 to, where's the line here? Like that? So probably, whatever. 5 to 7.5, so whatever it is. That's what I've said. I wouldn't worry too much about pH. As long as you're in the 5 to 8, you're probably fine. You try to start screwing around with it and start messing it, moving it down or moving it up, trying to line the soil, trying to put sulfur on the soil, trying to mess around with stuff. You better know exactly what the most limiting nutrient is. Have a good reason. And the good reason is, I see a turfgrass deficiency to whatever, iron, manganese, sulfur, whatever the case is. And I'm going to move the pH because this document shows that when I move the pH from 6 to 7 or 7 to 6, the plant uptake of that element is going to increase substantially. That would be a good reason. But just because you heard it at some conference that, oh, well, pH should be 6.5 and I'm at 5.8 and I'm at 5.5. Now I want to move it from 5.5 to 6.6 because pH of needs to be there for maximum phosphorus solubility. Maximum phosphorus uptake is probably right where you're at 5.5. Or it's closer to 5.5 than it is to 6.5 in most cases. So have a good reason. And phosphorus uptake, moving pH into the 6 to 7 range. I'm assuming you're in a normal agricultural soil. If you're in some bizarre soil where you got a pH of 9.5, that's different. Or you're down in the 4s, that's different. But if you're in 5 to 7, I wouldn't worry about moving the pH too much. If anything, if your intention is to increase phosphorus uptake, you got to get down to the 5s. Don't hang out in the 6s. Get down to the 5s. That's what all these data are saying. Okay? 6 and the 6.5 and 6.3 stuff is mythology. It's soil science mythology is what it is. All right, let's go. Let's continue. The effects of pH on decomposition of organic matter. Decomposition of organic matter is accelerated by increasing pH. Supply of both nitrogen and sulfur are therefore increased. This is consistent with the effects of low pH and decreasing the activity of microbes leading to accumulation of organic matter. Let's look at figure 12 right here. Figure 12 shows, for those listening, we have pH, calcium chloride pH from 4 to 7, in mineralization, CO2 evolution, and then sulfur mineralization on the y-axis. And we see from pH 4 to pH 7, all three, nitrogen, carbon, and sulfur, which are all mineralized from organic material, they all increase from 4 all the way to 7. Okay? So if you're up here at 7, 7.5, and you go, well, I want to reduce down the pH because the soil microbiology is better. It's between 6 and 7. Well, no. This is showing you should just stay where you're at 7. I guess this is 7.2 or whatever this is, 7.1, 7.2, whatever this is. You should just hang out at 7.2. If your intention is to increase nitrogen mineralization or increase sulfur uptake, if that's your intention, and you're going to lower pH from 7.2 down to 6.5 to do that, then this graph is saying, no, don't do that. Just stay where you're at. That's not a good reason. Okay? Let's continue. The effects of pH on nutrient uptake by plants. So now we're finally getting to the good stuff, and I'm an hour and 20 minutes in. The surface of plant roots also, this is going to be important. So if you're listening or you're watching, let's just take a deep breath, okay? Because we're going to get into the really, really important stuff. Okay, all the other stuff's been maybe a little bit, a little bit much. I don't know how you received it or not, but from this point forward, we're going to be talking a lot about plant uptake and how the uptake at the root surface influences the soil solution. Basically, is what we're going to be talking about. Okay, so let's focus for the next let's say 15 minutes. I'll try to knock this thing out of the park. The surface of plant roots also bear variable charge. Liu et al. 2020 measured zeta potentials of plant roots and showed that as the pH increased, the surface became increasingly negative. This means that the concentration of cations near the surface will decrease and the concentrations of anions will increase. There are also specific effects of pH on plant uptake mechanisms. The overall effect of pH on the availability of nutrients to plants are a combination of the effects of pH on sorption by soils and the effect of pH on plant uptake. Okay, so what he's basically saying is that, well, let me just make sure I was hoping to have one of these authors on so I don't screw it up, but let me make sure I'm getting my ducks in a row here. The surface of the root, I guess you want to call it, this root surface becomes increasingly negative. Okay, this means that the concentrations of cations near the surface will decrease. Why? Because the plant's taking it up. The surface is negative. The plant's taking that cation up into the soil solution and decreasing the concentration of the cation in the rhizosphere because it's taking it up. Okay. So the overall effect of pH on the availability of plants' nutrients is both the influence of soil sorption and the influence of plant uptake. So if it's being sorbed very strongly, if a particular anion or cation is being sorbed by the soil very strongly and it's not available for plant uptake, that's going to affect the plant uptake. If the plant if the pH is influencing the plant uptake, adjusting the pH or adjusting the potential for uptake of cations, that's going to affect the plant uptake. So the pH can affect those two. So it's a combination of what's sorbed in the soil and what the plant has access to, basically. Okay. pH on plant uptake and pH on absorption of these anions and cations by the soil itself. So we don't necessarily want the soil to have a strong sorption of these elements, because when it's sorbed on the soil, it can't go into solution, or it's not, well, it can, but I mean, it's not in solution if it's sorbed on the soil, and the plant won't take it up. We do want a CEC that can hold nutrients, cations. We want that. Generally speaking, that's desired. But we don't want it sorbed so strongly under the soil that it won't release into the soil solution and have access, and the plant have access to that. Okay? That's how the pH can affect those. But continue. Phosphate uptake by plant roots increases as the pH decreases. Let me repeat that. Phosphate uptake by plant roots increases as the pH decreases. So don't be moving your pH from 5.5 to 6.5 if your intention is to increase phosphorus uptake. I'm going to have to take a lozenge. When this was first observed, the rate of phosphate uptake was noted as closely matching the proportion of phosphate present as the monovalent ion, and it was thought to show that this was the ion taken up by roots. Subsequently, it was concluded that the mechanism of phosphate uptake involves the hydrogen phosphorus, the hydrogen H plus phosphorus co-transport, We are not overly concerned with the mechanism here. The important message is that there is a large effect of pH, so large that it dominates, at least above pH of about 5. The outcome is that phosphate fertilizer is least effective near pH 7. It is necessary to apply more of it to achieve the same yield as at a lower pH. It is most effective near a pH of 5. At lower pH, aluminum and toxicities decrease the response. I don't know how much more clear it can be said for phosphorus, guys. If you get down below 5, you're going to have some aluminum, toxicities. Not necessarily aluminum binding phosphorus and reducing phosphorus uptake. Okay. The greatest uptake of phosphorus is going to occur around 5. If you're going to have a pH of around 7, you're going to have to apply more phosphorus to get the same effect as if the pH was lower. Okay? The outcome is that phosphate fertilizer is least effective near 7. So don't be moving it from 5.5 to 6.5, or 5 to 6.5, or 5 to 6, or 5 to 7. Don't be moving it up if you're in the 5s, if phosphorus is the limiting nutrient. Okay? The behavior of aluminum is thus consistent with other cations. Its solubility decreases, pH increases. Okay. So when you're talking about aluminum and phosphorus binding or having phosphorus deficiencies at these lower pHs, it's not so much that as it is because phosphorus is going to be, the maximum uptake is going to occur at 5. Okay. It's when you get below 5 that the aluminum is actually just going to become plant toxic. It's not necessarily that the aluminum is going to bind the phosphorus and you're going to find some phosphorus deficiency when you get down there way low. Okay. It's the toxicity of aluminum. Let's talk about some other elements. Boron. I don't know why everybody's so interested in boron. There must have been some meme or something that came up on boron. I don't know. These two authors that I cannot pronounce their names in 1975 concluded that boron uptake by roots involves passive diffusion into the roots of undissociated and therefore uncharged boric acid molecules. It therefore differs fundamentally from most other nutrients, the uptake of which involves ionized forms in active transport. Most of the results of these authors were for fairly high pH values. If we extrapolate to the lower pH values of interest for uptake from soils, the effect would be small. This is consistent with the results of Peterson and Newman in 1976. They found little effect on boron uptake between 4.5 and 6.3, but a twofold decrease at pH 7.4. Okay, so that's about boron. Pretty simple, straightforward. Molybdenum. Uptake of molybdate occurs via phosphate binding transport sites at the plasma membrane of root cells. This means, like phosphate, uptake will be slowest at high pH. However, the effects of pH on sorption are so large that they dominate and the availability increases with increasing pH. Okay? These effects have been known for a long time. Lewis and Watson in 1942 reported that acidic fertilizers applied to the soil decreased tart disease in cattle. This disease is caused by excess molybdenum in the diet. On the other hand, Anderson and Moy, 1952, showed that clover growth could be improved either by applying lime or by applying molybdenum, a classic example of a negative interaction. Okay, so that's about molybdenum. Here comes sulfur again. Sorption of sulfate decreases with increasing pH. Figure 9. Do I have that in here? Figure 9? Did I go over that already? I don't know if I went over figure 9. No, I didn't go over figure 9. That's okay. We don't have time. We'll go over it next time maybe. Okay, the sorption of sulfate decreases with increasing pH, meaning there's less bound on the soil. And mineralization of organic sulfur also increases with increasing pH. On the other hand, uptake of sulfate by barley roots decreases with increasing pH. This is what he's talking about, the schizophrenic nature of it. There should be more sulfate available at these higher pHs, but the uptake of sulfur by barley roots at least decreased when pH went up. The This is another example in which the effects of pH on plant uptake are opposite to the effects of pH on soil chemistry. So there's sulfur that the uptake should be increasing as pH goes up, but it's not. Okay. The uptake of sulfate, at least by barley roots, went down as the pH went up, even though the quote unquote availability of sulfur increased. Mineralization of sulfur is increasing, right? The sorption of sulfate by the soil is decreasing, meaning there's more in the soil solution, but the uptake is decreasing. So there's a perfect example why that figure does not hold much water in my mind, because it shows that sulfur should be not limiting at these high pHs. Uptake should be high at these high pHs, but the actual uptake is not high at high pHs. Like I said, that's another example in which the effect of pH on plant uptake are opposite to the effect of pH on soil chemistry. So there's a perfect example of a macronutrient where the uptake is the opposite of what that graph shows. Now, here's another graph of phosphorus. I'm just going to show this real quick as I move through it. pH 4 to 7. In this case, we're looking at rice, mustard, and lucerne. We're talking about phosphorus in the tops of the plants, again, being maximized at 5 to 4.5, 5, something like that is where the uptake is being maximized. Here we see at the next panel above this, when the pH was maintained at 5.19, we see the tops, the growth basically being substantially higher than when the pH was 7.26. So in other words, the growth was greater at 5.2 rather than at 7.2. Okay? As a result of greater phosphorus uptake. All right, nitrogen. And, here, the exchangeable cations, potassium, magnesium, and calcium. So here's, I think we're getting to the end. We're getting to the end. So hold tight, guys. We're getting to the end. I knew this was going to be a long one because I'm not going to be back on for another week. So hang tight. These are the fun ones. Exchangeable potassium, magnesium, and calcium. Notice how he says exchangeable cations, not available cations. All right, here we go. These are the fun ones because these are the ones that are opposite. Two of these elements, or at least two of them, two of these elements provide further examples for which the effect of pH on soil chemistry are opposite to the effects of plant physiology. So if you look at that graph, you should say, wow, I should have no problem with potassium. pH is this. I have no problem with magnesium. pH is this. Well, let's see what actually happens for the plant uptake. As the pH is increased, the increased negative charge on the soil particle will mean that a smaller proportion of the cations is present in the solution phase, and the rate of movement to the plant roots by diffusion will decrease. Now, remember at the beginning, he was talking about permanent charges and variable charges. And what he's saying here is variable charges that can exist in any soil, and if the pH in those soils goes up, the increased negative charge on the soil particle, in other words, the soil particle will be increasingly negative. So the increased negative charge on the soil particle will mean that a smaller proportion of the cation is present in the soil solution. However, excuse me, sorry, I'm starting to lose my voice. So we're talking about this, a smaller portion of the cations is present in the soil solution, and the rate of movement to the plant roots by diffusion will decrease. However, uptake of potassium involves export of protons, and a similar mechanism would apply to magnesium. Uptake of potassium is therefore favored by high pH, as is uptake of magnesium. So what they're saying is that when the pH goes up, there should be less of these available. The uptake should also be reduced, but we don't see that. We see the uptake being favored, uptake of potassium and magnesium, being favored by higher pHs because of the manner in which the plant takes it up. Okay. The plant is exporting protons and taking up potassium, magnesium. So if you look at that chart, you're going to say, well, potassium, magnesium should be going down because these pH, in higher pH soils, the cation exchange capacity is going to be reduced. These negative charges on the soil particles means there's going to be fewer cations, smaller proportion of the cations is present in the soil solution phase. But we don't see the reduction in potassium, magnesium at these high pH. We actually see it being favored because of the function of the plant. And then he says, again, as far as we are aware, the outcome from these two opposing effects has not yet been measured. Okay. So there's three examples, sulfur, sulfate, potassium, and magnesium are all taken up by the plant at an opposing pH to that diagram, at a conflicting pH, I should say. If you look at that diagram, you say, oh, we should be deficient in sulfate at this pH. So the plant's going to have problems. Nope, not at that pH. We should have plenty of potassium, or we're deficient in potassium. You know, at these high pHs, we should be decreased potassium, whatever the case is. But the plant takes it up anyway. Okay? So now let's get to calcium. This is the BS artist's favorite element. If you want to know the telltale sign of a BS artist in soil fertility and selling fertilizers, it's calcium. Because calcium's always a problem to these people. Meanwhile, calcium's almost never a problem. Calcium's almost never a limiting nutrient. It's the major cation in all soils of agronomic importance. It's almost never limiting. But yet, you send a soil sample off to these grifters that sell stuff on base cation saturation, and everyone comes back basically, we got to apply more calcium. You got to apply more magnesium. It's nonsense. For calcium, there is usually such high concentrations in the soil solution that movement to plant roots is by mass flow rather than by diffusion, and the effects of pH on surface charge would be expected to be less important. The mechanism of calcium uptake also differs from potassium and magnesium. It is thought that it is taken up through plasma membrane channels expressed in roots and transported to the shoots in a mainly apoplastic way. This suggests it would be little affected by pH. Further, pH is often adjusted by adding calcium carbonate, so the effects of pH and calcium concentrations are confounded. So what he's basically saying there is whenever pH gets down that low, people throw lime on it, and that the issues get confounded because it's very likely or very possible that the effect at these low pHs is not due to a reduction or a deficiency in calcium, but probably a result of a toxicity of some other element like aluminum. But they just go out and throw calcium carbonate out there and they see a response to it and they go, well, the calcium was deficient. Well, in reality, it might not have been deficient. You may have alleviated the aluminum toxicity and thought you were eliminating a calcium deficiency. Okay. This is the classic, post hoc ergo propter hoc. You did this, therefore that happened, therefore that must have caused it. Meanwhile, you didn't even consider the other possibilities. And in fact, it was that possibility that was actually being influenced, not the one that you thought. Uptake of, so we're talking about zinc and other specifically sorbate cations, very short. Uptake of metal ions from solution by plants is increased by increasing pH. Uptake of metal ions from solution by plants is increased by increasing pH. This has been shown for zinc, for manganese, for cadmium. Okay. This opposes the effect of pH on metal sorption. Okay. Uptake of these metal ions from soil solution is increased by increasing pH. But increasing pH will generally show that those elements, or the availability, if you want to call it that, is reduced. One qualification. The relatively few measurements that have been made of the effects of pH on nutrient availability have utilized plants which, for want of a better name, you might think of as ordinary plants. By this is meant that plants have only small effects on the pH. These are plants that have only a small effect on pH of their rhizosphere. Little attention has yet been allocated to plants that have large effects on the rhizosphere. And then he talks about some plants that have a large effect. So what he's saying is this is quote unquote normal plants that kind of have just a normal influence on rhizosphere, but there are some plants that have a really magnified influence on the rhizosphere. They can really affect the pH. They can really affect the natural chelates that go out into the rhizosphere and have a much more profound impact. So it's not every plant is the same. Okay. Different plants have different abilities to influence the rhizosphere and in turn influence the amount of nutrients that get taken up into it. You can't just look at plants as rhizosphere. This is what's going to happen. You have to look at the plant as well as other soil factors. The conclusions. Effects of pH on availability of nutrients are complicated and diverse, but they do follow principles that we are beginning to understand. Nevertheless, too often theories have been advanced based on observations with model substances or with soils without regard to the effect of pH on uptake by plant roots. In some cases, these can be overwhelmingly important. Too seldom have theories been tested by actually measuring the effect of pH on uptake of nutrients by plants growing in soil. So if I can just sum this whole thing up, throw away the pH diagram, don't use it. We don't sell lawns and sell golf courses and make, our money on a soil pH diagram. We make money on plants taking up nutrients, basically, producing a product, and our product is a uniform sward and an acceptable sward. The pH diagram only looks at pH in some theoretically pure system that, is not reality. It's not in reality. It doesn't account for soil sorption or desorption. Doesn't account for the plant interaction with the soil, which is the major function. The plant interaction is what we care about. Getting the nutrient into the plant. Okay. Whether or not the element is, soluble or insoluble, it's important, but that's just one thing, just one variable in an immensely complicated system. Okay. If you're looking to adjust pH, have a good reason. Okay. And just because you've heard adjusting pH into 6.5 is the ideal range is not a good reason. That is not a good reason at all. There are cases where the most limiting element might be best available at 5, pH 5, pH 5.5, as in the case of phosphorus, what we just showed. There are cases where the most limiting nutrient might be better taken up or more easily taken up at pH of 7, as in the case of the lowlium species on that graph. So if you're going to adjust pH and you really want to be effectively efficient with your finances and your money and your program, you must first know which element is limiting the growth or limiting the quality or limiting the acceptable limit or level or whatever. If you know that, then we can start to, put money into certain areas to adjust the pH, either move from urea to ammonium sulfate, which we reduce the soil pH, over time, or apply a lime or whatever the case might be. But you need to have a good reason. And just because you heard it or somebody said it, or you've heard it on YouTube, or you heard someone say it on a presentation, doesn't make it true. Okay? There's clear cases where your attempt to alleviate a deficiency actually results in the opposite effect because you didn't realize that wasn't the limiting nutrient, it was something else, and it resulted in the exact opposite effect of what you're going for. Okay? So the soil pH diagram, unfortunately, has been around for ages, and I suspect it's not going anywhere. But if one of you today were using that, and today, after watching this, you throw it away, then I'll consider myself, happy. I'll be happy if just one of you change, because it's not a good approach. You need to know a lot more about what you're doing and what's going on in the soil before you decide to throw money at adjusting soil pH. Okay, I haven't. I mean, I grow a perfectly fine lawn here. I grew a perfectly fine lawn in Florida, and I've never applied anything to adjust soil pH, and nor did I even know what the soil pH was in my lawn. If there was a problem, I would take a soil sample and see if the pH was extreme, 4 or 9. These extreme values are clear cases. That's probably a pretty good reason to consider adjusting if you're in these extreme low or extreme high pH soils. But if you're in these ranges of 5 to 8 or 5 to 7.5, anything like that, I think the evidence would support me when I say I wouldn't worry too much about adjusting soil pH unless you have a very specific, clear-cut deficiency, and moving the pH would very likely alleviate that deficiency. Okay? I'm going to go to the chat, and then I'll let you guys go. There's a lot of chat tonight. Very good, guys. Appreciate that. If you want me to answer something, please throw it in there. I'm going to try to scan through the chat, see if I can catch something that might be particularly interesting. While I'm looking, if you guys, I'll be in Florida on the next Monday and Thursday, giving a talk up in Daytona. If you want to come, say hello or listen to a lecture I'm giving. I'll be in Daytona, Florida for basically most of next week. No, Chuck, there's no quiz. The end. I would probably fail that quiz, so no. Yeah, I don't see anything. I'm so apologize if I missed something, but hang on, let me look here. Oh, that you're asking somebody else something. Okay. Guys, I'm gonna let's see here. Yeah, Gray, I empathize. That's what I said at the beginning. The paper is actually very general. It's a very general language paper for a soil chemist or soil mineralogist. I'm not either one of those. I'm a soil fertility person, but chemistry and mineralogy are in my world. I have to understand the basics of these things in order to have some sort of, confidence in what I'm saying. So it's very general language, believe it or not. But I know for the average person, it's relatively complex. At the end of the day, soil sorption, soil desorption, organic matter mineralization, all these things play an effect. But the plant also plays an effect. Okay, the plant is very good at doing what it's doing. It's evolved over millions of years, and it's very good at doing what it's doing. And throwing materials and resources to adjust pH is usually futile. It's usually temporary. And if you don't know what you're doing, you might not have accounted for potential adverse consequences by doing that. Okay. So, I'm not an advocate for just looking at a number on a pH, test. I'm at 5.8. I'd rather be at 6.3. Well, why? Why? And if you say, well, phosphorus is more available at 6.3. Nope. That's not what the evidence says. The plant uptake of phosphorus is probably better where you're at 5.5 than it would be at 6.3 in many cases. Okay, so I understand and empathize why you might think that, because you've been hammered. It's been hammered in your mind and your brain so many times. Oh, calcium at high pH and aluminum iron at low pH. And so we want to be at 6.3 and 6.5. That's where we want to be. It's been ingrained into our, DNA almost to this point where we're wired a certain way. But to soil scientists, this is nothing new. I mean, simply adjusting pH to do these things. And in fact, that other article had a best sentence. If you, in fact, let me get it back up. It has the best sentence I think I've ever read at the end of a conclusion. Let me pull this thing back up. It's fantastic. Let me get back to this. This is the last sentence of the previous article. It's great. Raising the pH to say 6 to 7 might be justified for several reasons. Completely agree. There may be good reasons to do that. but increasing it for the availability of phosphate is not one of them. Okay, that's not a good reason to increase your pH to 6 to 7 if you're in the 5s. If you want more phosphorus or uptake of phosphorus by your plant, and you're in the 5s, leave it alone. Okay, that's the message from that last article, and we're going to go over that article too. It's a much more simple article than this article was. And Chuck, your comment there, I'll take you up on. I'll take Ryan up on it. I don't. Maybe I'll email him before I get on the plane or something to see if we can do something from Daytona. Maybe we can do it from like the diner or something. We can do like a phone cast or something. I don't know. So anyway, guys, I really appreciate all the chat. We had a good group on tonight, and I know that article is quite lengthy. It's quite detailed and it can be quite cumbersome, but it's all in video. Watch 5 minutes of it, pause it next time, like and subscribe, I guess. Okay. Thanks for everybody that subscribes and follows me. I appreciate it. Just watch 5 or 10 minutes, listen to 5 or 10 minutes, pause it, rewind it again. I mean, that's what I do with videos and books. I mean, you can only grasp so much at a time. You start losing it, just put it aside and come back later, All right, guys, tonight I have some music from my favorite jazz artist, believe it or not. This jazz artist is the daughter of one of the most influential musicians in history. Okay. I think she's actually more influential than he, or better than he was. But her father was acknowledged by the Beatles to be one of the most influential factors in their music. The Beatles actually went to India to study under this artist's father, and they learned a lot from, particularly George Harrison, learned from this particular woman's father. And I've seen her many times. I've seen her in Tampa. I went to Orlando. I think I even saw her in Rome once. I've seen her live many, many times. And it's very light. It's for the last show before I take a little week off in Daytona. Very light music. But I appreciate everybody showing up. Some nice little jazz music as we say goodnight. I really appreciate everybody showing up. I'll be back in a week or two if I don't pop on from Daytona. Okay? Thanks. See you guys. Be kind. Bye-bye.